Hi Calculus. We're viewing this video after Tuesday's class, and it's 10:11 that you'll be watching it. Call this section of your comp book higher order derivatives. So it won't take long to explain, so let me be about that. So when we have higher order derivatives, we are going to take an example such as y equals x cubed plus 2x, and we're going to take the first derivative, or the derivative, and we get 3x squared plus 2, according to using the power rule in both of those terms. Now that is called the first derivative. Guess what happens when I ask for the second? I get 6x plus 0, I won't write that in. And can I take a third derivative? That's going to be the derivative of the second derivative. And can I take a fourth derivative? The derivative of any constant is 0. After that, all the higher order derivatives will continue to be 0. So first derivative, second, third, fourth derivative. So another way I can write that, well, we've seen dy dx. I've seen dy with a 2 dx and dy with a 3 dx and dy with a 4 dx. And I've also seen these multiple primes for fourth, third, second, and first derivatives. So why would you want to take the derivative of a derivative? Well, there's plenty of times where that is practical. Let me show you one. Here's the position function of an object that is falling on the moon. So we have a position function, and when we take that, maybe it wasn't falling, maybe it was being tossed on the moon. It looks more quadratic. So a position function where it was tossed on the moon, and the first derivative, we learned earlier, is also velocity. So I take the derivative of that, and I get 2 times negative 0.18 t, and that is negative 1.62 t. And then the second derivative is going to be the derivative, the second derivative is going to be the first derivative of the velocity, and that is, guess what? Acceleration. So the second derivative of the position is acceleration, negative 1.62 in this case. All right, so the first derivative from a position function is velocity, and the second one is acceleration. What if you took the derivative of acceleration? Some of you know. Well, we'll discuss that tomorrow. All right, but I'll give you a clue. I won't be a jerk about it. All right, that was higher order derivatives. Since that was so short, we're going to do a second topic. And that is, keep the video down. I'll have you do part of it for me. We'll do derivatives of other trig functions. We've done the derivative of sine and cosine. So let's go ahead from there and see what else we do. Say y equals tangent x. Were you wondering what the derivative was of tangent x? Well, now that you've had the quotient rule, you can find out. So y prime, well, first of all, y, we'll redefine it as a quotient. So our old friend, tangent is sine over cosine. So y prime is going to use the quotient rule. So low d high minus high d low all over the square of what's below. Low d high, the derivative of sine, minus high d low. So the bottom times the derivative of the top minus the top times the derivative of the bottom all over over the bottom squared. That's the quotient rule. So let's clean it up a bit. We get cosine squared x plus sine squared x, and sine squared x plus cosine squared x is an old familiar friend. It's a 1. So we end up 1 divided by cosine squared. So when possible, we write all our trig expressions without a fraction line. So 1 over cosine squared is the secant squared. So when you have y equals tangent x, y prime equals secant squared x. Alright, interesting. Alright, let's go ahead then and look at cotangent. So if that's tangent, let's look at cotangent. I'll just leave that up and erase underneath. Alright, so if I have y equals cotangent, I remember my trig IDs that is cosine over sine, and y prime is going to be using the quotient rule from there. So I'm going to see if you can establish that on your lonesome and bring it into class tomorrow. So here's what I give you. Y equals cotangent x, and you give me y prime equals something. So use the quotient rule like I did with the tangent, and you will get the derivative of the cotangent. Alright, I'll do one more and you'll do one more, and we'll call it a night. Let's say I'm going to do y equals secant x, and I'm going to do that as 1 over cosine x. So I'm going to use, it's a quotient, so I'm going to use the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And so simplified, that is positive sine x over cosine squared x. And again, we want to try to get the fraction sign out of there. So this little trick you can use when I ask you to do the cosecant. And we're just going to regroup sine x over cosine x and 1 over cosine x. See how these two sides are equivalent. These two expressions are equivalent. I just pulled apart the cosine x and regrouped it. So sine over cosine is tan, and 1 over cosine is secant. Usually we write it secant tan. So I'll do that up here. It's my third one. If y equals secant x, then y prime equals secant tan. Secant x, tan x is usually the way we write it. So guess what you get to do? Y equals cosecant x, which is 1 over sine x. Use the quotient rule and you will have its derivative. Alright, that's all for tonight. Bring these valuable facts with you and principles, and we'll put them into action. Till then, bye-bye.